Okay. Lecture 75, Phase Transitions. Name and describe the different phase transitions. So, I just put all 6 up here. Solid to liquid would be melting, liquid to solid, freezing, those are pretty common. Liquid to gas is vaporization. Gas to liquid and gas to solid are both condensation. And gas to liquid can also be called liquefaction. And gas to solid can be called deposition. And then solid to gas is sublimation. Okay, hold on. So, you should know those terms, what they mean. See, I think there's... Oh yeah, and then melting can also be called fusion. Just to finish that off. Okay. To describe vapor pressure and show the relationship between vapor pressure and kinetic energy. So, most liquids, well, pretty much all liquids, I guess, to some degree or another. If you have the liquid, so we'll have water here. There's a certain number of water molecules that will go into the gas phase. And after a certain amount of time, you'll get the same number of gas phase molecules entering the liquid phase as liquid molecules going into the gas phase, and you reach an equilibrium. Well, since you have these water molecules in the gas phase now, they are exerting pressure on the walls of the container, so that's your vapor pressure. Now, it's not the pressure of the gas, where the liquid has turned completely into a gas, just a small amount of it has, because it has some extra energy. So, and that's the second part here, says show the relationship between vapor pressure and kinetic energy. So we have kinetic energy here, and then this is the number of molecules. So we don't mark it off, but the graph, if we draw a graph like this, then though we're not saying how many there are, we know that if we're here, this is twice as much as here, which is twice as much as here, so it's just a relative scale. So this is T1. We have a range of kinetic energies. Some molecules are moving very fast, and some are moving very slow, and some have almost, very few of them have come to a complete stop. Now, there is a kinetic energy, this point, this is the minimum kinetic energy to escape. The escape from the liquid phase. So you can see that most of the molecules don't have enough energy to escape. A small portion of them do. And to escape, they also have to be at the surface. So there's at the surface, there's this, the way I've drawn it here, looks like somewhere around 10% of the molecules have enough energy to escape. So we have a pretty high vapor pressure because of that. As the temperature goes up, though, we get more molecules moving faster, so we get a higher percentage that have the minimum escape kinetic energy. So let's see, this is T2. So the number of molecules that are in the gas phase that have escaped from the liquid phase is higher, so the vapor pressure goes up. So as the temperature increases, the vapor pressure increases. And then they say, and between the rates of vaporization and condensation. As I said, we reach an equilibrium. So if you look, if we compare, or we have time versus the rate of vaporization is constant at the surface, assuming the temperature doesn't change. A certain number of gas molecules are escaping. So if we put a liquid into a container, the rate of vaporization goes on at the same rate continuously. In the gas phase, though, we put more and more water molecules into the gas phase. We're assuming water here, but it can be for any liquid. Eventually, you have so many water molecules in the gas phase, or H2O molecules in the gas phase, that they start making their way back into the liquid phase. So there's, at first, the rate of condensation is 0, but then it builds in. So we have the rate of condensation. And when those two are equal, we're at equilibrium. And there is a set number of water molecules in the liquid phase and in the gas phase, and that won't change, even though the water molecules, H2O molecules, are going back and forth between the phases. There's an average number that remains the same. Okay, so, and at equilibrium, that means the rate of vaporization and the rate of condensation are the same. Okay. Draw the heating curve of water and show all the important features. This one is used, let me make sure, yeah. This is used in standardized exams a lot because it's a picture. Chemistry doesn't have a lot of pictures that we can work with, in graphs that we can work with at this level. Mostly it's equations, so anytime you get a graph, the people who design the tests very often seem to latch onto that. So the heating curve of water comes up a lot, so you shouldn't recognize it and the parts of it. So we're adding heat at a constant rate over time, and we start with so they have a temperature of minus 20 degrees Celsius, and then didn't leave a lot of room here. We'll say 0 and put the, so 20, I'll say 40, and then 80, and then this would be 100. Just didn't leave any room on the other side. That's where I would have put them, but put these temperatures. But we start out with the ice, and this is as the temperature rises, the H2O remains as ice, but the temperature is increasing as we add in more heat. But then at 0 degrees Celsius, for a short time, we have ice and water together, and the temperature doesn't change. That's the really important thing. At a phase transition, we're putting in heat or taking heat out. We could always go backwards on this curve, but as we add heat or take it away at the phase transition, there's no change in temperature, even though the heat is being, in this case, added. So that's really important. That's what they'll focus on, and what I'll focus on this curve. That's very important, is what's happening at this plateau. Then once all of the ice has melted, and then we just have water, and the water just increases in temperature linearly. And then we reach 100 degrees Celsius, and we hit the water and steam portion. And then after all of the water has been turned into steam, then the steam starts to increase in temperature. So at the plateaus, here and here, the heat energy goes into breaking bonds. When it's ice, it's a solid, so we're breaking the lattice, the energy that holds that lattice together, and then it's loosely held together by hydrogen bonds after that, and dipole bonds that we'll talk about later, as water. So the water just keeps increasing in temperature and moving faster, but then eventually those hydrogen bonds and the dipole bonds and the van der Waals forces are broken. And now the water is completely free. The H2O molecules are completely free. But at this point, where there's a plateau, the heat doesn't go into raising the speed of the molecules, and that's what the temperature is. Instead, it goes into breaking bonds. In these points on ice, water, and steam, it's going into kinetic energy, into making the molecules move faster, either vibrate faster in the solid or move faster. Tumble over each other faster as water, or just move around the container free as for steam. So that's what you should know about these points. Now since the temperature doesn't change, we can't use this. We've used this before to register the amount of heat that goes into, in this region here. We'd use this equation. But at this point, where there's no change in temperature, then this delta T would be 0, so we can't use this. Can't use at a phase change. Instead, we use for this one here, we use what's called, from solid to liquid, we use the heat of fusion. And from liquid to gas, we use what's called the heat of vaporization. And we'll use that in the next problem. And for water, the heat of fusion is 6.01 kilojoules per mole. So we just need to know how much water we're using, and we can determine how much heat has to go into breaking all of the ice up into water at that temperature, which is 0 Celsius. And then the heat of vaporization is, for water is, okay, so the heat of fusion, this is delta H FUS for fusion, and then delta H VAP for vaporization. This is 40.7 kilojoules per mole. Don't need to know those or memorize those, but you should know what heat of fusion and heat of vaporization are. They're different. The values are different for different compounds. We use water so much that you may end up knowing it just because you use it a lot. Okay, so let's take a look here at a problem where we can, an actual calculation. So the heat of vaporization of ethanol, so we'll put delta H VAP, is equal to plus 38.4 kilojoules per mole for ethanol. For every mole of ethanol that we want to vaporize, that we want to take from a liquid to a gas state, it's going to require 38.4 kilojoules. Now, we don't often work with 1 mole of ethanol. We work with whatever we have, and they tell us here it's grams, 505 grams. So convert that to moles, multiply by this term, and that tells us how much heat had to go into vaporizing the ethanol. So we want to take ethanol liquid and change it into ethanol gas. And ethanol is C2H5O. So I'm not sure why I'm not using the formula. That's what we want here. So the heat of vaporization for this is plus 38.4 kilojoules per mole. All right, so the mass of this thing, so it's 24, it's 46 grams per mole. So that's 24, 29, 30, 40, 46, yep. So what we do is we take the 505 grams. There's a second part to this problem too, but let's focus on this first. It's 46 grams for 1 mole of it. And then for every mole, you need 38.4 kilojoules of energy to vaporize, to change that 1 mole from liquid to gas. Ethanol we use as a solvent or a cleaner in our labs. And that's the basis, ethanol's basis for alcoholic beverages. So you have 422 kilojoules of heat. Now, that's how much energy it took to vaporize that ethanol. Then the second question is, how many grams of water at 0 degrees Celsius could be frozen to ice at 0 degrees Celsius? Okay, so we have... and they want to point out that we're changing from 0 degrees Celsius to 0 degrees Celsius. So we need to use the heat of fusion for water, which is 6.01 kilojoules per mole. Now, that how many grams could be frozen to ice by evaporating? So we had to put this energy in. This energy had to go into the ethanol. So if we took that energy out of the ice, or out of the water, that should freeze some of the water, assuming the water is at 0 degrees Celsius. So we took the energy for ethanol out of the water, and this is how much water, and this is how much energy we took. So if we take that 422 kilojoules, and then every 6.02 kilojoules, and this is for H2O, if we take that energy, and that energy came out of the H2O, for every 6.01 kilojoules of energy taken out, 1 mole of water will freeze. So it's this. And again, we're assuming that we're right at 0, so we don't have to use that Q is equal to S times M times delta T equation. Though there may even be a problem in the back of your book where you have to use both of them. We're not going to worry about that. 1 mole, not here anyway. And then 1 mole of water is 18 grams of water. I should have water all along the way. So let's see how much. So for 422 kilojoules of energy, we can freeze 1.26 times 10 to the third grams of water. So this is a two-part question. This is how I put it on the exam. You have so many grams of ethanol, or whatever it is. It could be ammonia, whatever the other compound is. Convert to moles. For every mole, we have this much heat that is used to vaporize it. Here's the total amount of heat that went into vaporizing the ethanol, the 505 grams. Then we take that amount and we put it into this expression. We try to determine how much of the water was frozen. So for every mole of water frozen, we needed 6.01 kilojoules of energy. So we convert that energy to moles and moles to grams, and there you go. Now, what's this one here? So we have the normal boiling point for ethanol is 78.1 degrees Celsius. The heat of vaporization of ethanol is 38.4 kilojoules per mole. What is the vapor pressure of ethanol? Now this is the Clausius-Clapeyron equation, which is this form, or this equation here. And what we're doing is we're determining the vapor pressure at a different temperature, or at a certain temperature. Now, it doesn't look like when we do this out like we have enough information. We're going to say P2 is what is unknown, and it looks like we don't know what P1 is either. The heat of vaporization is 38.4 times 10 to the third joules per mole, and we need to have that because our R constant is going to be 8.31 joules per kmol. And then our T1 seems like it's unknown, and well, actually our T1 is the boiling point of ethanol, so 71.223. This is 351 Kelvin, and then our T2 is 21, so that's 294. Now this is the boiling point of ethanol. This is the trick that we use. When ethanol is boiling, or any liquid is boiling under atmospheric pressure or standard atmospheric pressure, the pressure then is 1 atmosphere. So at this temperature, ethanol boils, and ethanol is then going to reach the pressure of the atmosphere, and we're going to take that to be 1, so that simplifies things. But they don't want to know, so that we know for sure, for any liquid that boils, and then now we want to know the vapor pressure at 294. So we do 351, then 294. Just going to do this quickly because we're running low on time here. Times 38400. And I get natural log of P2 over 1 is equal to minus 255. We want a negative there because this P2 needs to be smaller than 1. And if you don't see that, that's fine. But what we do is take the antilog of both sides. So this is going to be P2 over 1 is equal to e to the minus 2.55. So it's the antilog, or the second function of the negative, of the natural log. And we end up with P2 is equal to 0.0779 atmospheres. And because we're running low on time, I'm going to double check this, and if I'm wrong on this, I'll just tack it on to the next problem, but it seems reasonable at this point anyway.